So once we've identified our parameter, what it is we're trying to estimate, next we need to check the assumptions that need to be true in order for our calculations to actually make sense. We're going to be doing some calculations using a black box in the calculator, and we need those calculations to make sense. The reason for these conditions is highly technical, and we're not going to go into it at the moment. And this question is a little bit tricky because the notation for describing these questions is much more complicated than the concept of what they mean. So this is what we'll use. These checks that we're about to do is what we'll use if we want to construct a confidence interval for qualitative data, right? So we need to note that we're talking about qualitative data, qualitative information. And we're trying to construct a confidence interval for a population proportion. So here's the conditions in words. So the big idea is that it's not the case that almost everything in the population has one or the other of the possible qualities. So we need to say our sample is big enough to contain at least 10 yes answers. So our sample, so we have at least 10, in the context of this problem, cash transactions. It's also big enough to contain at least 10 no answers. And so the way to think about that is neither yes answers nor no answers are super duper rare. We didn't just accidentally miss seeing all of the cash transactions, or we didn't just accidentally miss seeing all of the non-cash transactions because our sample was too small or because they're too rare. And then the other assumption that we need is that our sample is small relative to the population. The reason we need that is very technical and mathematical. And the rule that we give for being much smaller is that the population is 20 times as big as the sample. Or more. Okay, so these are the assumptions that we're actually checking. But we're not writing the assumptions in words. We're writing the assumptions in mathematical symbols. And the other thing that we need to know is how we actually represent these. So looking at these symbols, right, The variables that we see are P, right? That's the population proportion or percentage, right? This is all cash transactions in our case, divided by all transactions. P hat, that was the sample proportion. That's cash transactions sampled divided by all transactions sampled. N, that's the sample size. Right, that's the number of all transactions sampled. And big N, that's the population size. That's just all transactions. Okay, so how do we put our assumptions in terms of these symbols? Well, by putting N and P hat together, we can get expressions for the number of yes answers and the number of no answers. P hat is the number of yes answers divided by the sample size. So if we take the sample size times P hat, that gives us the number of yes answers. So that means condition 1 can be written as N times P hat is greater than or equal to 10. Now, there's a little bit of algebra involved in this next part. You can either work through the algebra on your own or take my word for it. If we take N times 1 minus P hat, we get the rest of the transactions. We get the number of no answers. So condition 2 can be written as N times 1 minus P hat is greater than or equal to 10. And then condition 3, we actually have symbols for everything in that. The population size is big N, the sample size is little n. So condition 3 we'll write as big N is greater than or equal to 20 times little n. Right, so it's very hard to remember these if you try to memorize them in terms of the symbols. Right? Think about what they mean in words. There are at least 10 yes answers. There are at least 10 no answers. And the population is big relative to the sample. Okay, and now we're going to actually check these. So we have in the problem our sample size is 1,750. Our cash transactions are yes answers. there are 437. And then that's all we're given, right? So we'll need to figure out something about the no answers. And we'll need to figure out something about the population size. But here are yes answers. That's our NP hat. There are 437. And that is, in fact, greater than or equal to 10. Right. So condition 1 is met. Now the no answers, well, the transactions that were not in cash, right? That's all the transactions minus the ones that were in cash. Our calculator is our friend here. We take 1750 minus 437. We have 1,313 transactions that were not in cash. So that's our n times 1 minus p hat. And again, that's greater than or equal to 10. So we have enough yes answers, we have enough no answers. And now we need the population size. We need to know something about how many sales transactions altogether there were in the US. I don't know, last year or something. The problem doesn't tell us that. And that seems like it would probably be hard information to get, right? Just counting all of them seems like it would be hard. So we have an instruction here. If no n is given, use this big number, 1 followed by 6 zeros. Right? That's 1 million. Right? Use 1 million is what the problem tells us to do. And the reason that we can just do that is, I think you'll agree that there were definitely more than 1 million sales transactions in the US last year, right? The population of the US is something around 300 million. And most people made more than one sales transaction last year, right? We don't actually care about this number. We just care that it's big enough. So we'll use 1 million. And we want to compare that to 20 times little n, right? That's 20 times the sample size, 1750. Again, our calculator is our friend. We have 3,500. Or no, I'm sorry, 35,000. I can count zeros. And we see that 1 million is greater than or equal to 20 times our sample size. Right. So since we know the number of sales transactions had to be at least 1 million, the population must be more than 20 times our sample size.